So when so in this chapter we are studying system of particles. So we studied the topic center of mass. So what is the center of mass? Center of mass is a point. So when we calculate the center of mass, we find the coordinates of this point. Okay, means x, y, z. We write them with capital letters. And what's the center of mass? What's this point? This point moves as if all mass is concentrated. All mass of the body, all mass of the particles is concentrated at it, at center of mass. And all the external forces are applied at that point. Means F is equals to m a. So A is the acceleration of center of mass. This A, this capital A. So earlier we were writing F is equals to ma, right? So this is for a particle. This F is equals to ma is the formula for a particle. Okay. So small a, small m. But here capital M and capital A. Of course, internal forces cancelled out each other, so this is always F external. So that is the center of mass. That if we are applying a force on the system of particles, so we are not studying the motion of all the particles. We can only study the motion of one point, which is your center of mass. And we assume that the external force is acting on that point and whole mass. So this whole body is has mass m, and we have a center of mass, suppose, of this body over here. So this O is the center of mass. So assume that this is point O, and this O has mass m, highly concentrated, like you have what do we which heavenly body do we have in the universe? Yes, which is highly concentrated? Black holes? Yes. Are you aware about the black holes?
Yes, sir.
Okay. So they are highly very high density. So this is equivalent. So this extended body with mass m and has the center of mass O, you can assume that this body is equivalent to this point mass. Okay, this extended body, system of particles, this body is equivalent to this particle. Okay, so O is the position of the particle and m is the mass of the particle. So this is equivalent to this. So that is the center of advantage of center of mass, meaning of center of mass, that you are assuming this extended body as a point mass. So this is you can say it as point mass, and this point is your center of mass. So assume when a force applied on the body, we assume that the force is applied on this center of mass. Okay. Now the next topic we are going to study is center of gravity. So what is center of gravity? So when you talk about center of gravity, It's also a point. It's also a point which has the coordinates, of course. So what's the specialty about this point? Like, you can balance your notebook on one finger. Can you do it? In the class, students used to do in the free time. They just hold this notebook on their fingers or on the tip of the pencil. Yes, can you see this figure? Figure 7.24 in your books. Yes or no?
Yes, sir. Yes, sir.
So you are balancing a cardboard here on the tip of the pencil, and the point of support, which is G, the point where pencil and cardboard meet, that point G is your center of gravity. So G is the point which is center of gravity, and at this point there is a complete mechanical equilibrium. Yes? So center of mass, where we assume that the whole mass is concentrated at that point, and center of gravity is the point that if we are balancing that object at that point, there will be no rotational motion, there will be no translational motion. So that is center of gravity. Okay, is this clear, students? Center of gravity, very simple. Yes, it is related with gravity, so you need to hold it, hold that object. So you can find the center of gravity of any object. Just hold it on your finger, and if it is balanced, there is no movement at that point of the object is stationary, that point is the center of gravity. It's so simple. Center of gravity means at that point when you are balancing that object on the tip of your finger or on the tip of your pencil, then that point of support is the center of gravity. So we have complete mechanical equilibrium. So it's so simple now. You have understood both center of mass and center of gravity? Yes, any problem? Yes?
No, sir, it's clear.
It's clear?
Yes, sir.
Okay. Do you want me to read from the book, or is it okay? Shall we move forward? Shall we just make the notes? I think you can give a reading through the book yourself. Okay? Now, let us see example 7.7. So 7.7, you can see this figure. We have to show that the moment of the couple does not depend on the point about which you take the moments. So where you are taking the torque. So suppose this O is the origin here. So this O can be here, this O can be anywhere. Can be here, can be here, can be here. O can be anywhere. Okay? But it is not going to have any impact on the moment of the couple. Okay. So what is the moment of the couple here? What is the net torque, you can say, acting on this? So it's a couple. So what I told you, what forms a couple? First thing is, for the couple you need two equal and opposite forces. And second thing, for the couple you need, what is the second thing here? Yes, Vinay, what is the second thing? Second condition to form a couple. Vinay is not there. Vinay Pudir, yes.
Yes, sir.
What is the second point? Second condition for the couple. Yes. Harsh Swami.
Sir, different lines of action.
Excellent. Very good. Very good. Very good, Harsh. I told you yesterday also that there should be different line of action. So see, this is the line of action of this force and this is the line of action of this force. You can see they are parallel. They are never going to meet. So different line of actions, parallel lines of action. So these are the two things that you need, and it results into rotational motion. Okay, there will be no translational motion because the forces are equal and opposite, but there will be rotational motion. Good. So let us consider a couple. This is your couple. So we have the two equal and opposite forces along different line of action. The forces F and negative F. Okay, if it is plus F we are taking, so of course this equal and opposite we are taking it as minus F. They act at point B and A respectively. These points have position vectors R1. So position vector of point B and point A. So this is origin. So position vector R1 and this is the position vector R2. Let us take the moments of the forces about the origin. Okay. So means now what is torque? Torque, you know, torque is equals to R cross F. So R is the position vector from the point about which you are going to take the torque, about where you are going to take the moment. So we are going to take the moments about this point. Okay, on this point about which we are going to take the moments. So what is the position vector from this origin? That is R. So this R1 cross F. So this is your F, and that's your angle, you know, R cross F. So put your fingers on R and move them towards F. So your thumb will point inwards or outwards. What is the direction of the torque here? Yes. What is the direction of torque? Is it into the plane of the paper or is it out? Sangeeta? Yes, Mansi, yes. Huh? Into the plane of the paper?
Yes, sir.
Sangeeta? Agreed?
Yes, sir.
And what about this case? Torque at this point B. So this is the force, this is your position vector. See, here we have to extend this R1. This is the direction of R1. So this is not the direction. Okay. So what is the first thing that we need to do? We need to extend this direction. direction of the position vector, and then when they are both the vectors are joined by, you can say, tail, then we are going to take the direction. Yes, so that's the direction now. So that's the angle that we are supposed to take. Yes, students?
Yes, sir. Yes, sir.
That's the angle that we are going to take. So this is the angle theta here. So of course this angle is not, this is not the angle that we are going to take. Always we are going to take that this is a vector A and this vector B. So they are joined by their tails, and this angle theta that we are going to take. Okay? So extend this, and now this is the angle theta. And now curl your fingers from R to F. So what is the direction? Yes? Veena, what?
Outside the paper.
Coming out, you are late today. Eh? So coming out of the plane of the paper. So student, don't fall into the trap of the earlier one, like this angle is right from R to F, you are joining. Don't fall into this trap. Is this okay?
Yes, sir.
Okay. Now what about this here, the angle? This is where is the angle in this case now? What's the angle?
Outside. Oh, inside the paper.
Yes, this is inside now. Okay, so this is outside and this is inside. So here we have this R2. Okay, this direction R2. So R2 to F. So here you can see that this direction is from here to here. This theta was clockwise, and here theta is anti-clockwise. Okay, is this clear? Again, so what is the net torque? Net moment of the couple is the sum of the moments of two forces which are making the couple. So R1, so that's your R1, yes, cross minus F. So R1 cross minus F plus R2 cross F. Okay, that is R1 minus R1 F sin theta, R2 F sin theta, their magnitudes. Okay, now R2 cross F minus R1 cross F. So reversing the distributive law, you can take cross F common. So don't do this. This is not equal to F cross R2 minus R1. So don't take the common this way. This is wrong. Okay, this is wrong. So F is means on the right hand side, so F will remain on the right hand side. Okay, because this cross product. So you know that A cross B is not equal to B cross A. The direction is different. Magnitude is same, but direction is different. So that is why writing the cross. So this is not multiply, this is cross, because these two are vectors. So cross product. So R2 minus R1. Now what is R2 minus R1? So this is your R2, this is your R1, and so what will be, what side will be this? What will be this side? This is R2 minus R1. See, I told you earlier also, you want to reach this point B. So one way is directly from you are telling the direction of this point B from origin, okay, or you are telling the relative position in respect of origin. If you are telling, then it's simply R2 vector. But if you are telling it position of R with respect to position of point B, you are telling the position of point B with respect to point A, okay, with respect to this point A. So first of all, this relative position, so its position with respect to origin minus its position with respect to means the position vector of B minus position vector of A, okay. So this is one way of understanding it. Another way you can find it from triangular law of addition. Reaching O to B directly R2, so O to A, R1 plus you add this, so R1 will cancel out and you will get R2 only. So this simple thing is, this is your, suppose R2, this is your R1, and we are reaching here from this point to this point, so you can call it delta R also, okay. So this was your initial position A, this is your final position B, so that's the displacement, okay, that's the origin. Always join these arrow, students, always they are supposed to be joined. Now what is delta R? Delta R is final position minus initial position, okay, and you can find it from triangular law also. That's the same thing. This R1, so you started from origin R1 and then plus delta R, so initial position plus displacement, you reach the final position, that is your R2. So you can understand it in terms of relative position of so position of B with respect to origin R2, position vector of B with respect to A is your, so that's what your delta R is. So from here also you find delta R is equals to R2 minus R1. So delta R is R2 minus R1. Okay, got this, students? So what is this R2 minus R1? R2 minus R1 is nothing but this vector AB. Yes, this delta R you can write, okay. Is it okay? So AB cross F. So what is the torque acting in this case? So net torque acting in this case is equals to AB cross F. Students, this is very important formula. You will need it in chapter 1 in class 12th also. So very important. Tau is equals to AB cross F. Okay. Is this clear?
Excuse me, sir.
Yes.
Sir, at point B, what is the direction of torque? It is maybe outside the paper.
Yes. It is coming out of the plane of the paper.
So both of them, they are outside the paper.
No. Yes. Yes. Absolutely right. Both the direction of theta is anti-clockwise in both the directions, so both ways it is coming out of the plane of the paper, and that is why it will rotate. So in which direction it is going to rotate? It is going to rotate, yes,
Anti-clockwise.
Anti-clockwise. Yes, very good. If the directions will be different, then they will cancel out each other, okay. Then there will be translational motion. Yes, if both the forces were in this direction, this is this F and this again F, so both will be, so there will be translation motion in this direction, okay. So now the forces are equal and opposite, so they form a couple. So in a couple, we have no translational motion. We have only rotational motion. Okay? Another concept related with the couple. So students, got this question? So this is independent of the origin. So this formula tau is equals to A B cross F. So this couple, the moment of the couple, which is A B cross F, does not depend on the point about which you are taking the moments. So O can be here, O can be here, it doesn't matter. Because why? Why it doesn't matter? Because this is your relative position. This is not, AB is not the position from the origin. AB is your relative position of B with respect to A. So it doesn't matter where you are taking this. This will always be the same. Okay.
सर मेरे को नहीं आ रहा है.
Yes.
एक बार दोबारा बता दो सर.
आप just tell me one simple thing. If you are taking this this point as origin, okay, and these are the position of A and B from this point. So is this displacement going to be changed? The action or the magnitude? If you are taking this as origin, displacement is independent of origin. Displacement does not depend on origin. Yes, have you read this point? Same is the case here. If you are taking this as origin, then this is the position vector of A, this is the position vector of B, but the displacement will remain the same, the relative position of B with respect to A. So I am taking this because these 2 points are fixed, A and B. Forces are applied at these 2 points. Line of actions are fixed. So here in this formula, you are taking AB, position of B with respect to A. So AB means position of B with respect to A you are taking. So it is independent of origin. You can see in the formula also. Is this, have you understood this point or not? Still you have not understood this.
Thank you, sir.
Yes.
So if we take origin at the line of AB only, then what will be the force?
See, there are this point, suppose B. This is point A. I can tell the position of point B 2 ways. Position of B, okay, 2 ways. First way is with respect to origin, okay. So this is the origin, this is the position. So this is the position vector OB, okay. This is the one way to tell that to reach point B, and I call it, suppose, R2, okay. So I can say it OB also, I can say it R2 also, that's the same thing. Now I can tell the position of B with respect to another point which is A. So that's the point A. So this position. So how will I tell this position? So I'm telling you the position vector, position of this with respect to A. So I'm reaching B. So I was reaching B from O. Now I am reaching B from A. So right here A. Is this clear? And this AB, so you are telling the position vector of B, but with respect to A. So you have to subtract the You have reached A first. Instead of directly reaching B, you have reached A first. So you have to subtract this, the position vector of A from here. Here you were subtracting the position vector of O, that was 0. So that remains R2. So and that we write position vector of 2 with respect to 1. That's how we write it. So is this concept clear? So this is R21 you can write. You can write it as delta R. You can write it as AB. All the three ways you can write this vector. And this is equals to R2 minus R1. This. So tell me, is this AB depends on the point where you are taking O? Suppose these are the points A, B. Okay. See, what is the meaning of AB? Don't get it confused with R2 minus R1. The both will change. This origin. Okay. This is R2. This is R1. So tell me, is AB changed? A and B points are fixed. See, A and B, these 2 points are fixed. So AB vector means what? Its magnitude is equals to AB, it will remain the same. And its direction is, suppose this is x-axis, this x-axis. So this will also be x-axis. A and B are fixed. A and B are fixed. Okay. So magnitude of AB, yes, direction along x-axis. So this vector is not changed. This vector AB doesn't matter where you are taking origin, doesn't matter. Is this clear? See, this question is something like, these are 4 points. Let's suppose origin O. This distance is, suppose, 20 meters from this point. This is O, A, B, C. This is 50 meters and this is 75 meters. Now I have moved from B to C. I have moved from B to C. So B to C. Now what is my displacement? If you are taking origin as O, okay, so displacement is final position minus initial position. So what is my final position here? So final position is OC minus OB. So OC is 75 meters minus 50 meters. So the displacement is 25 meters. Okay. Now I am taking the, so here O was the origin. So origin was O. Okay. You took O as origin. Now I am taking A as origin. Okay. I am taking A as origin. Now I am taking A as origin. Okay. Now tell me, delta x, here also it was BC, here also it is BC, this length is BC. So that's final position minus initial position. Now what is the final position? Again it is C, but now I am taking A as origin, so AC minus AB. So what's AC? AC is 55 meters. What is AB? That's 30 meters. What is the displacement? 25 meters. So does the displacement depends on the origin?
No, sir.
मानसी बेटा समझ आ रहा है आपको?
हाँ सर, मुझे आ रहा है.
हाँ? मानसी, is it clear to you?
यस सर, आ रहा है, बट बीच में थोड़ा मतलब डाउट है.
See, displacement is independent of the origin. Any vector that you are considering, so here we are simply considering the vector AB. So AB, this vector will remain the same irrespective of the origin. Okay?
Yes sir.
So students, this is what we have done. The formula of torque is AB cross F. This you can simply find that as this with this formula. Now we have discussed center of gravity. What is center of gravity? Center of gravity is also a point, and at that point of it's a point of balance. So center of gravity is a point of balance. So you are applying upward force at that point, so that's the point, and you are applying upward force at that point, and the gravitational force means acting on the whole body is actually is balancing, you know. So like you are balancing the cardboard. So this is the cardboard that you have, and you have the tip of the pencil, and the whole cardboard is balanced on the tip of the pencil. So this G is your center of gravity, where you are pointing this, where your pencil and the cardboard is in contact. So this point of contact is point of support here. So this is supporting the cardboard. So point of balance, or you can say point of support, is your center of gravity. So you are supporting this whole cardboard, so it is not moving, no translation motion, no rotational motion. So at this point G, if we make a free body diagram of this cardboard, so the force acting on the cardboard, one is due to the pencil, which is the reaction R. This R is due to the pencil. So forces on the cardboard, this is due to pencil, and this is mg, that is due to gravitational force. This is due to earth. So earth is pulling this cardboard down. So this R is equals to mg. So this, the magnitude, of course they are equal and opposites, so but their magnitude R is equals to mg. Their magnitude are same. So this is this point of balancing, this point of support is center of gravity. Okay, So this tip of the pencil provides a vertically upward force due to which the cardboard is in mechanical equilibrium. So at the point of balance, at the point of support, the body will be in a mechanical equilibrium. So center of gravity of a body is the point of balance where the body is in a mechanical equilibrium. Okay? The reaction of the tip is equal and opposite to mg, and hence the cardboard is in translational equilibrium. It is also in rotational equilibrium. So the center of gravity of the cardboard is so located that the total torque on it is not rotating. So the total, so different particles are there on this cardboard. So all of them are being pulled by the earth, but they are cancelling out each other. So no rotational motion. Yes, we have studied it in one of the figures also. Yes, which figure we are talking about? So students, you need to keep the figures in your mind. We are talking about figure 7.20a. Yes, this is just like 7.20a. So there is no rotational motion. So these forces are the torque will cancel out. So the torque in this direction and the torque due to this will be in this direction. So the rotational motion due to this, yes. So movement of both the forces will cancel out each other. Figure 7.20a. So similarly they will be cancelled out. So no rotational motion. Why there is no translational motion? There is no translational motion because I'm holding it at the point of balance, and the R is equals to mg. Mg is the weight of the whole cardboard. Okay. So the net gravitational torque, that is R cross F. So F is mig. So I is for particular particle, and adding all of them we get the rotational torque 0. And as the G is non-zero, so we are taking the condition here that G is constant for all the particles. Means all the particles are being pulled by the earth with the same acceleration due to gravity. So G is same. So that's the condition I'm taking. So if G is same, G comes outside and this comes that, and G is not 0. So it means MIRI is equals to 0. Okay. So if I have this cardboard, there are two ways to find the center of gravity. So this is one of the way, just holding the tip of your pencil with that cardboard, it is balanced. Okay, that is your center of gravity, this point. Now what about so this point was your center of gravity G. Now what about now you are determining the center of gravity of a irregular shape. Here also the shape was irregular, and now what you are doing is you are suspending this body. Okay, so first of all suspend it from A. So the center of gravity will lie on this line, on this vertical line A dash. Okay, now suspend it from B. Okay, so it will lie on this line B1. Now suspend it from C, so it will lie on this line C1. So they are similar concept that we did like for the center of mass, that for the triangular lamina. So if we divide it into strips, so it will lie in the midpoint of the strip, center of mass, midpoint, and then you what is the common line? So this line, so center of mass lies on this line, so then we divide it into this way and then on this line, and then means on all the three medians the center of gravity was going to lie. So the common point of all the medians was the centroid. So centroid was the center of mass of the triangular lamina. Remember? So similarly the case here. center of mass lie on this vertical line, center of gravity lie on this vertical line, on this vertical line. You can hold it like I am holding it from here. So where will this lie? This will be the vertical line. So it will pass through this. So the center of gravity lies on the vertical line, okay, through the point of the suspension of the body. So from that point draw a vertical line where you are suspending the body. So we get this center of gravity. So if you hold it at tip means from this point, if you are holding this body, it will be in mechanical equilibrium. So the center of gravity of the body coincides with the center of mass. So center of mass and center of gravity is the same if in uniform gravity, means if the value of G is same at all the points. Okay, if G is same at all the points of the body, then means or gravity free space, means G is equals to 0. So then also, so that's the same thing. So G is same, G is 0. So the center of gravity and center of mass. Center of mass, you know, center of mass is the point where we assume that the whole mass is concentrated at that point and the external force is acting at that point, and we study the motion, means the velocity, the acceleration of that particular point. Okay, and the motion of center of mass can only be changed by the external forces. Is this clear, students?
Sir, why do we need center of gravity?
Why do we need center of gravity? See, center of gravity is a point, okay, where you are balancing this cardboard. Suppose I want to balance this cardboard on the tip of this pencil. So at which point I will point my finger, means this pencil, balancing the cardboard. If you want to balance the cardboard, where will the tip of the pencil will be? So that is center of gravity. And more we will do in the following example. Why do we need the center of mass? Okay, center of gravity, why do we need? Okay, so look at this question. So these are the two examples that are related with the center of gravity. So we have a metal bar over here, and this metal bar is 70 centimeter long. So this AB length, this AB is 70 centimeter long. Okay, so this G, center of gravity, will of course, see, there is this rod is of uniform, this uniform rod, this metal bar. So its center of mass will be there at the midpoint, and as as there is uniform gravity, so the center of gravity will also lie this point. So center of mass and center of gravity will be the same. Okay, so now why do we need, you are asking, why do we need center of gravity? See, this center of gravity, okay, this whole weight of the body is means this W is because this rod, this is the rod, okay, and I can balance this rod at this point G. Okay, this is your point G. So the whole, you can assume this is the mass of the rod and this is G. So here you can assume that the weight of the body, you can assume it equivalent to a point mass. Okay, and that point mass is G, and the whole mass of the body is, so the both these cases are, so you take it as rod, and you take a mass particle M which is located at G. Okay, so this is mass particle. Just like in case of your center of mass, you were assuming that this is the mass, this is the center of gravity, and whole mass of the body was considered at this center of mass. So what was the advantage there? that any force acting on this point, we were assuming that all the force is acting at that point. Okay, so that is the point mass. So here also it is a special case of you can say center of mass. Center of gravity is a special case. We are assuming only one force. So here you were assuming force from any direction, but here we are assuming the force only in a downward direction. So you can say this is a sort of special case of center of mass. So here for center of mass we were applying force from any direction, okay, on this mass, but here we are assuming that we are only applying the mass, means we are only applying the gravitational force. So center of gravity, we deal with only gravitational force. We assume that the whole mass of the body is concentrated at center of gravity and it is being pulled down. Okay, so now if I want this point to be stationary, so that's the another thing. Now if I want this point to be stationary, what I will do? I will apply equal and opposite force in this direction. So I am holding it, so the reaction force will be this R. Got it? Center of gravity, you can assume that the body is being pulled down by the whole mass is concentrated at this point and the body is being pulled down by the earth m into g. So at this point you have to apply the equal and opposite force, that is your reaction force, mg force upward you need to apply, then only it will be in equilibrium. Is this clear? So this mg I am going to write it as weight of the body. Okay, now here we have 70 centimeter long bar and 4 kg is the mass suspended over here at two knife edges. So we have the masses, these are the two masses that are so metal bar 70 centimeter long and 4 kg is the mass. So mass is 4 kg of this rod. So this rod has mass 4 kg. Okay, so this whole, so it is being pulled by the earth at this point G, and that is pulled by mg. That is the weight. So that is equals to 4 into G, which is 9.8. Okay, so that's the advantage of center of mass. That is the application of center of mass, that we assume that the whole weight of the body is actually is over here. पर उसमें भी सेंटर ऑफ मास में भी आपके पास क्या एडवांटेज था? You were considering F is equals to ma, whole mass of the body. Where you were studying the acceleration, where you were studying where the force applied on the center of mass. So here also this rod is being pulled by the earth from this point. Okay, okay, see, you can watch the video again if there is any problem, and we can discuss the doubts tomorrow also. We are not in a hurry. Okay, see here, so this is the metal bar. It is 70 centimeter long and 4 kg mass. So it's at the center of gravity. At this point we assume that it is being pulled down, this rod, by the center of gravity, that is this. Okay, now next thing is that the mass is supported on two knife edges placed 10 centimeter from each end. So this is 10 centimeter. This distance AR1 is 10 centimeter. This distance R2B is also 10. So this is 10. This is 10. I have written it already. 10, 10, 10. Now A 6 kg load is suspended at 30 centimeter from one edge. So from one end, this is one end 30 centimeter, and I have suspended this 6 kg load. This is W1. So the weight of this 6 kg, what is the weight of this 6 kg? 6 into 9.8 is the weight, that is your F1 being pulled by the earth. So this is the load I have suspended over here. This is the load. This W is the weight of the rod. So this is related with the rod, and this W1 is related with the load. Okay. Find the reactions at the knife edges. So we have to find what is R1 and what is R2. This is what my question is. And we have to assume the bar to be of uniform cross section and homogeneous. So it means uniform density. So G is same throughout the means this is what we are going to assume. Okay. So for translation equilibrium, yes. What are the vertical, means for translation equilibrium, of course we see that sigma fx is equals to 0, sigma fy equals to 0, means net force in x direction is 0, net force in y direction is 0, net forces in z direction will be 0. So is there any force in x direction? There is no force in x direction here. So there is no force in x direction. What are the forces there in y direction? Yes, we have there is no force in z direction. We have the force only in y direction, means in vertical direction, right? So what are the forces? So as the rod is in equilibrium, so in translation equilibrium, sigma fy is equals to 0. So let us see. So upward direction we take positive, and downward direction we take negative. So what are the upward forces? Write the upward R1 and R2, reactions due to the knife. Okay, so R1 plus R2. And what are the downward forces? So downward forces are this. This load is being pulled by the earth by the force W1, and the rod is being pulled by the earth with the weight W. So these are the two downward forces, one weight of the load and one weight of the rod. Okay, so the net is 0. So what is W1? 4 into 9.8. What is W? 6 into 9.8. So this comes out to be take G is equals to 9.8. So this is minus 10G. 10 into 9.8 is 98, and this will come this side, so it will become positive. So this is the first equation that you have got. R1 plus R2 is equals to 98. Now consider the rotational motion, rotational equilibrium. So take the moments of the forces about what point? About G, about this point G. We are going to take the moment of the forces, means this is the origin we are considering, and point where we are applied the forces. So this is the position vector we will be taking from G. Okay, so the moment, so here again anti-clockwise moments we are going to take positive, and clockwise moments we are going to take negative. Now wherever we have the forces, we will find the moments at that point. Okay, torque acting at that point. So where do we have the forces? Like, let us start this. These are the four forces, of course, R1, R2, W1 and W. So these are the four forces. Let us find the torque at that point. So R1, so what is, so torque is equals to, so the magnitude of torque is R into F. So if it is in this direction, torque in this direction, take it as positive, in clockwise take it as negative. Okay, so R into F. So this R1, R is the force acting on it, and what is its distance from the point where about which you are taking the moment? So that's point G, origin we are taking G. So R1G. What is the distance? So R1 is 10. So R1G will be 25. This whole road is 70. So this mid is 35. Take 10 out. So you're left with 25. So this is R1G is 25. So R1G, sorry, this R1 is the force and the point we are taking as K1. So K1G. So K1G is 25. And students, all the units we are supposed to take in SI units. So this is in centimeters. So that is equals to 0.25 meters. So kg, I have put the value of kg. Now second is W1. So same R into W. So that's 0. The distance from the G to point P into the force. Force is W1. So the distance is 5 centimeters. So 5 centimeter means 0.05 meters. So put the value of PG here. Now the next force is your W1 you have taken. So W is the next force. Now in case of W, tell me what is R into F in case of W. So force is W. W means the weight. But what is R here? R is 0. So the moment of G is moment of W is 0. Is this clear, students? Yes. Torque at point G. So R is 0. So moment of G is 0. Sorry, moment of W, moment of the force. Okay, so moment of W is 0. Now let us take the moment of R2. So simply force, what is the force? R2 into the distance from G. So that is 25. So R2 and this is in meters, 0.25 meters. So K2G is, so K2G, this distance is 25 centimeters. So 0.25 into R2, that's equals to 0. Okay. Now solving them out, and this W1, what is W1? Yes, W1 is the means 6, this is the load, 6 into G, 6 into 9.8. so W1 is 6 into 9.8. so 6 into 9.8 will comes out to be taking 0.25 common, dividing it out. So this will comes out to be, you will find that after solving this you will find that R1 minus R2 is equals to 11.76. So you have two equations, R1 plus R2, R1 minus R2. So solve these equations, simple linear equations, you will find the value of R1 and R2. So this was this example 7.8, and you can try the example 7.9 also. That's also simple. See, we have a ladder over here. This is the ladder AB and its weight is 20 kg. So here this D is the center of gravity here of the ladder. So its feet rest on floor A, and which is at a distance 1 meter from the wall, and we have to find the reaction of the forces on the wall and the floor. Means we have to find F1 and F2. So this is the reaction. So this wall is actually frictionless. Okay, students, it won't take more than 5 minutes. Just focus on it. We already have understood the concept. So this frictionless wall, so when the wall is frictionless, so in that case the reaction force on the wall will be perpendicular to the wall. So whenever we have a frictionless wall, so this angle will be, this reaction will be 90 degrees. So that's the condition. Okay, so now tell me the force acting on the ladder. The force acting on the ladder is the weight which is acting at the center of gravity. This is the first force which is acting on the ladder. Second force, the reaction force due to wall. I told you that this is perpendicular. And the third force is when the this ladder is applying the force on wall, so wall will also apply the force on that's the reaction force. And then the third is the reaction force F2, which is of the floor. Okay, so now reaction force of the floor will be actually, if it is means in this direction, this is inclined at angle alpha, so means this force will not be vertical over here, F2. So because this is not a frictionless floor, because the friction is being provided to prevent this ladder from further moving. So we have, this is the important thing, only important thing to understand here is this is your F2. This is your F2. Okay, the reaction force due to the floor on the ladder. So we have to resolve this F2 into two components, horizontal and vertical components. So this component, which is its x component, this component is your frictional force. This is your frictional force which is preventing this ladder to fall. So this we are taking here as frictional force as capital F, and this is the vertical component of this F2, and this we are taking as N. So students, this is the only thing that you need to understand. Now you know the vertical forces and you know the horizontal forces. So here we have this the forces in the vertical direction, N and W. So N and W. So these are means N and W, and as it is not moving, so translation equilibrium in vertical direction means sigma Fy equals to 0, and here in the horizontal direction you have two forces, that is F1 and F. So these are the two forces, F1 and F. So F1 is in this direction and F, you know, is in this direction. So here Fy means the normal force. This was your force W downwards, and the normal force was acting upwards. So you can make this force also. So this is your F1, this is your F, which is frictional. So the net will be 0. Plus and minus sign simply means upward direction positive, downward direction negative. This direction you are taking positive x, and this direction you will taking as a negative. So you will have two equations from here, and then a rotational motion taking the moments of force about it. So you can take the moment from all the four forces. So taking the moment about N. So but you are taking the switch off your mic. Randhir, better switch off your mic. So just have patience. So this is for the translational equilibrium. Here we have force on the x means along the x-axis and along the y-axis. So taking the, so here force along the y-axis we have taken 0. Here force along the x-axis we have taken the net is 0. So, and for the rotational motion, taking the moment of forces about A. So we are taking the origin as A, students. So we are taking the forces from A. Okay. So this is the so you have to take the distances from A. All the forces distance from A. Okay. So let us start from N. So N is at A. Okay. N is at A. So what is the advantage of taking, so you can take the origin anywhere, we have studied, but what is the advantage of taking the taking the moments of forces about A? The advantage is that you have two forces starting from A. Okay, like this force, frictional force, and this normal force. So both the forces, this frictional force and this normal force, so for both of them R is equals to 0. Okay. So that is why we are taking it as A. So for N and F, R is equals to 0. So torque is equals to 0 for both the cases, N and F. Okay. So N and F has gone. Now you are left with W and F1. So now W and F1. So W and so its distance from the from this distance you need to find out. And so which distance you are supposed to take? You are supposed to take the vertical distance. So this is your line of action, right? This is your line of action, and this is the where you are taking the distance from origin. So origin to line of action, this distance is so this is half of it. So this is 1 meter, this is 0.5 meter. So that's 0.5 meter. So about F, so about W, that is written as half. And what about F1? What is the distance of F1? So this is F1, and you are taking the what's your line of action here? This is your line of action, and this is your point from where you are taking the moments about A. So this distance is, so the distance between the origin and the line of action. Okay, so this distance you are going to take. So this distance is nothing but this distance BC, and that you can calculate. BC is equals to hypotenuse square minus base square. So that is root 8, and that is 2 root 2. So this distance is 2 root 2. Okay, so 2 root 2 into F1, and then you know that this means this direction rotational means this direction you are taking positive, and the clockwise direction you are taking negative. So taking this positive and negative sign, so this is this direction is direction of the moment of the force will be anti-clockwise, and this is clockwise. So that is why negative here for this. So simply you have 3 equations now. Okay, so calculating the value of W. So what is W? W is the weight of the ladder, that is 20 kg into 9.8. So put the value of W now, and that will be also your N. Okay, so W is equals to N. You can see here, put the value of W is equals to 196. So plus minus 196 will come this side, and it will become plus 1. So putting the value of W, you find the value of N. Okay, so from using first. Now what is W1? W1 is equals to, put this value of N in third equation. So this is your third equation. Put the value of N over here, means put the value of so students, you can solve these equations. Time is running out, it's 8 o'clock. So simply put these values over here, and you will get the answer. And this angle is alpha, so this angle is alpha here. So this is N, so you find N and F, and then you can find tan alpha also, the direction of your F2. Okay, so that's all for today. Thank you so much. Just revise this concept well. I will post the video also. Okay, okay students, you can leave the class. Thank you so much.